All right, so this is our first set of notes. So we are going to start with chapter 2. And in particular, we're going to be doing objective 2, but also part of objective 3. And the basic derivatives with a little bit of velocity accelerations as well. That's an R there, like a B. So I will capitalize my R. So chapter 2, objective 2 and part of 3a. So this is kind of our basic derivatives. So what do we need to remember? So just a reminder that when we are doing derivatives, remember that is the slope of our tangent line, right? So it calculates the slope of a tangent line. So that was from last year, right? So we talked about what a tangent line was, and we certainly know what slope is. And we also refer to it as a rate of change, right? So that was kind of two things that we looked at and explored, regardless of what class you came out of, right? So derivative is the slope of a tangent line, or it gives us that equation to find the slope of a tangent line, and then also rate of change. So the rules that we're going to be looking at, so the very first one is power rule. And again, this is something we worked with last year, so this is just kind of a review of that. So notation, so if we take that derivative with respect to x, that's that notation, and we have a variable to a power. So one thing that we're always going to be paying attention to, or not always, but we should be, is that if this is with respect to x, that means that variable there should be x as well, okay? For right now, like we're going to incorporate more of that kind of difference later on. So like perhaps this would be a t where that would be an x, then we have to do things a little bit different. Okay, but for right now, these will match. So that rule that we had to learn was we take that power, so that power is in here, and we multiply it to the variable, so the variable is x, and then we reduce the power by 1, and that was our power rule. Okay, and so just kind of a quick example just to make sure of that. If I have the derivative of x squared, so I would take that power of 2 and I would multiply it to my variable, which is x, so I'd take that 2, multiply it to x, and then I would reduce the power by 1, so 2 minus 1 is 1. So then my derivative would be 2x. Okay, so that's a very basic one, but that would be what power rule would look like. And then our other would be the derivative of a constant, which actually kind of falls into that power rule category. And I will show you just in case. So if I take the derivative of a constant, so we'll just say c is my constant. So c would be a number like 1, 2, 3, 4, 5, pi, or something like that. So that derivative of a constant would be 0, okay? And we're going to say 2 reasons why. So 2 reasons why is a derivative of a constant 1, right? So this is answering why, or why is it 0? Not 1, 0. Okay, so constant. So let's start with power rule reason. So if I had a constant, whatever that is, I can always write that out as c times x to the 0, right? Because x to the 0 is 1, and c times 1 is c. So these are equal, right? These are equal. So if I go to take that derivative using power rule, I would take the power, which is 0, times c, which is 0, and then reduce the power by 1. So that would be x, and then to the negative 1. And then 0 times x to the negative 1 would just be 0. So there's one reason, just using power rule. So the second reason, so this is another way to think about it, is remember that a derivative is the slope of your tangent line. It is a rate of change. So if I take a look at y equals c, so that is just the constant, right? So the graph of that graph would be, it crosses the y-axis at c, wherever c would be, right? I don't know where it is. So I'm just going to say, I don't know, let's call right here c. So we'll say that's my constant. So that would be a horizontal line, right? So that would be the graph of y equals c. So if I think of this as, okay, so it is the rate of change or the slope. Well, what is the slope of that line? So it is a constant slope. There is no rate of change. It is forever flat, right? It's not going up and over, up and over. It is a flat line. And so that derivative would be 0 because the slope of that line would be 0. Okay, so there's 2 reasons why that derivative of a constant is 0. Okay. All right, and the other two rules that we need is product rule. So for product rule, we're taking a look at trying to find the derivative of the product of two functions. Okay, so my two functions are f and g. So that rule, okay, so I'm just going to do it under here. Okay, so the derivative here is I take this equation here, f of x, and then I multiply it to the derivative of that. So the derivative of that, so a notation reminder, that would be when we use that apostrophe, right? And we would say g prime of x. So I take that original function and multiply it by this derivative, so that would be g prime. And then I'm going to add that to the kind of the reverse idea. So the reverse idea meaning I take g of x now, so its original form, and then I multiply by the product of the derivative of the other function. So if you look at this rule, I have an original times a derivative, and then the other original and the other derivative. Okay, so that would be product rule. So there is kind of a little, I don't know, chanty little song that you can sing with this as well. So this would be, I'm going to call f of x my equation 1, and then I'm going to call g of x my equation 2. Okay, so this is equation 1, equation 2. So if I look at this rule right here, so this is equation 1, and then I'm going to multiply that by the derivative of the second function. And I'm going to use d to mean derivative. So d2 means derivative of 2, which is the second function. And then plus, of course, is plus. And then that's equation 2, and then times the derivative of the first function. So the derivative of the first function, I'm going to write that as d1. Okay. So if I have two functions, 1 and 2, I can think of the product rule as 1d2 plus 2d1. So 1d2 plus 2d1. You don't have to sing it. You can just say 1d2 plus 2d1. Okay. And then our very last rule that we're going to work with is actually our trig rules. And since we know like a lot of trig functions, I'm still just going to call it as one trig rule. And there's just two that we're going to work on for this particular lesson. So the first one is sine. So if I take the derivative of sine of x, that would just be cosine of x. Okay. And then if I were to take the derivative of cosine of x, that would be negative sine of x. And then we could actually prove this a little bit with our limit definition that we did last year. And normally we would take a look at that, but this year time is short. So we're just going to say, ta-da, there it is. Okay. All right. So those are our rules that we're going to be working with. And the last component, so let's take a look at the last little bit. Okay, so this isn't really rules so much as it is application. So this is the application, or one of many, there's a lot of beautiful applications, but application of derivatives. So like, why would we ever use them? And one of the main ones we study is velocity problems, okay? So our standard notation is we're going to use S of t to be position. And when we get into the parametric component, which is in the second semester, we'll actually use like x of t and y of t because we'll specifically say like it's horizontal or vertical. But I'm just going to do that for right now, just in case I accidentally get into old habits and I throw in x of t or y of t. So S of t is considered position, but x of t and y of t is also position. So this would be a particle moving just left and right only. So it's not going up, not going down, left, right only. And this would be a particle that is moving up and down only. So no left, no right. So up, down only, left, right only. Okay, S of t can be potentially left and right or up and down, but it also could be a combination of the two. So going like kind of angly. So then v of t is our velocity. And in particular, we find that by taking the derivative of position. So remember, derivatives are rates, right? So position is like static, right? I am right here, boom, 12 inches away from my dog cam. And then my velocity is that movement, right, that is created. So that velocity is like, oh, look, I'm moving my hand. My hand has velocity, right? So, and it has direction. So if I go forwards or backwards, that's important, okay? So it is super important that we understand that piece right there, that velocity has direction. So that's not speed, right? So speed has no direction. So if we're going 30 miles an hour, it doesn't matter if we're going north 30 miles an hour or south 30 miles an hour, we're just going 30 miles an hour. Our velocity, however, does have direction, so that is going to always be important. So what do we need to know about that? So that means if velocity is greater than 0, we are headed right, because that's a positive direction, or we're headed up. Okay, so right or up. So that would be referring to kind of that component there. Whereas if velocity was negative, then we are headed left or down. So what's happening if it was just 0? What does that mean? It means we're taking a pause. We are resting. Okay, so we are resting. All right. So then our last little tidbit here is acceleration. So that would be A of t. Acceleration. So then we know that so acceleration is the rate of change of velocity. So like how, are we speeding up at all, right? So are we always 30 miles an hour? Probably not, right? So that means we had to get up to speed, right? So we had to go up to speed, and that is what acceleration is doing for us. So it's a rate of change of velocity. So how fast is velocity changing? And so that would be v prime of t, and then that would give us a of t. So then just on a side note, so if I have to take the derivative of velocity to find acceleration, that means I'm taking 2 derivatives of position, right? So 2 derivatives of position. So a double prime, that means I'm taking 2 derivatives, so the derivative and a derivative again. So that's what that means. And then that also is acceleration. Okay? All right, so let's go ahead and do a few problems here. So this is just going to be now just practice. So that's just kind of the information, and now we're just going to do a couple of practice problems just to kind of see, where we're at with things. Okay, so we're going to start with just like find the derivative. So the first one, we'll just say y is equal to 7x squared minus 2x plus 5. And so I'm going to put an implied 1 here just to remind me that there is a power of 1. So when I take that derivative, so I'm going to just do y prime, switch colors here, y prime. So this is power rule, so I take the power, which is a 2, and I'm going to multiply it to that 7. So 2 times 7 is 14, and then I reduce the power by 1. Same thing here, so I'm going to do negative 2 times 1, so take the power, multiply it to negative 2, so that would be negative 2, and then reduce the power by 1, so 1 minus 1, so that would be 0, and then a constant, its derivative is 0. So I don't need to write plus 0, I'm going to just for the sake of this very first problem. And then I want to simplify a little bit. I don't need to go crazy with the simplifying, but I'm going to do just a little bit here. So I don't need that power of 1, so that would be just 14x. X to the 0 is just 1, right? So that would be 2 times 1, so that would be minus 2, and I certainly don't need to write plus 0. So there is my derivative. All right, let's do another one. So we're going to do 8, and then I'm going to do the square root of x plus 1 over 3x. And then I'm going to get fancy here, and I'm going to go plus pi cubed. Okay. All right, so I always want to make sure that I rewrite this because I cannot use power rule. So power rule is specific to where it has to be a variable to a power. It is okay if there's a number in front, but you can't have that variable in like the denominator. It's got to be like there's a number, a variable, and a power, and that's it. Okay. So this is, I always have to put it into this form, right? Power rule has to be in this form. So I'm always going to want to rewrite so that I get it into this form, right? So it is important that I rewrite everything. So this is the form, or I cannot take a derivative. Well, cannot, I mean, like with the skills I have. Like we're going to learn more, but for now, like that's what I have to have. So that is going to be my first step, is I'm going to rewrite. So then I'm going to rewrite this. So this is going to be 8x, and then to the 1/2 power, because that's what a square root is, plus, and then this is just 1/3 right here, right? So that is just like the 1/3. So 1/3, and then x to the -1. Okay, so 1/3, and then you're just changing the variable, right? X to the -1. So the 8, you're just changing the variable, x to the 1/2. And then plus pi cubed. So I took no derivative, right? That was just my first step, is I want to rewrite. And then now I can take a derivative. Okay, so let's go ahead and do that. So y prime. So I'm going to do power rule here. So I'm going to do 1/2 times 8. So half of 8 is 4. And then subtract 1 from the power. So that would be to the -1/2. And then now multiply 1/3 times -1. And then subtract 1 from the power. And then, although this doesn't look like it, pi cubed is a constant, right? So this, although it doesn't look like it, this is a constant. So we will not do power rule, because what is my variable? Pi is not a variable, it's a number. So that would just be 0. So I can write plus 0, but I don't have to. So I can leave my answer like this. I don't need to rewrite it, but just for the sake of like any multiple choice, I'm going to do a little bit of rewriting. So a -1/2 power is going to go in the denominator, and it will become a square root. And then -1, 3 is in the denominator, x to the -2. So then that's going to be x squared. Okay, so then that would be what I have there. Okay. All right, so then now I want to take a look at kind of a combination. So I'm going to do a little bit of the trig and a little bit of the product. And so we have another one here. So I'm going to do 2x plus 5, and then I'm going to multiply that by sine of x. Okay. So right here, I want to go ahead and do product rule. And how do I know I'm doing product rule? Because I have a product of two functions that have variables in them, right? So there's a variable here and a variable here. So this is going to be product rule. So I'm going to label this 1 times 2. So that's a 1 times 2. So I'm going to be using y prime. So y prime, so product rule, 1d2 plus 2d1. So 1d2 plus 2d1. So here's 1, so equation 1. So I leave that guy alone, exactly the same. So because this one's left alone, then the other one I have to take the derivative of. So the derivative sign is cosine. And now plus, and now do the same thing again, but flip-flop which one you do. So now I'm going to leave this one alone, so leave this one alone. And then take the derivative of that. So I'm going to put a power there of 1. So that derivative, so 1 times 2 is 2x, and then subtract 1 here, so that'd be 0. And then 5 is a constant, and the derivative of a constant is 0. And then I'm going to do just a little bit of simplifying here. I'm not going to go crazy, just a tiny bit. So this, I don't know. I don't think I can do anything fancy with that to make it look better, so I'm going to leave it alone. And then here, though, this I can do quite a bit with, right? So x to the 0 is just 1, so that would be 2 times 1, so that's 2. And then plus 0, of course, is that. So, and then I could like write that as 2 sine of x, which is probably, you can see nothing in my screen, can you? Let me scooch that up. I'm sorry. so 2, that would just be x to the 0, which is 1. And so I could rewrite that as 2 sine of x, but I'm not going to. Okay, so what did I do again? I did 1 d2 plus 2 d1. And if you want to sing with me, 1 d2 plus 2 d1. But that tune always changes, but there you go. Okay? All right, so there's just some kind of like super, super basic derivative ones, but we will do more practice with that in class, of course. And so then now I want to do a couple of applications. So, and by a couple, I mean one. So let's take a look at an application problem. Okay. All right, so let's say that we have, so this is our application. So this is our velocity ones that we're going to do. So we're going to be given a position function. And we're going to say that it is negative, I don't know, 12t squared plus 4t and then plus 6. Okay. So the first thing we want to do is, so the first question will be find the velocity function. So find v of t. So for me to do that, I need to find the derivative. Okay, so I'm going to find the derivative. So v of t is the derivative of s prime. So that would just be power rule. So I'm going to do negative 12 times 2. And then subtract 1 off the power, so 2 minus 1. And then I'm going to put an implied 1 there. And then plus, and then power rule here, 4 times 1 is 4. And then subtract 1 off the power, so that would be 0. And the derivative of a constant is just 0. So then I have v of t is negative 24t, and then plus 4 times 1, which is 4. And then for question number 2, let's find a of t. So a of t, so is how velocity changes, so that would be v prime of t. So a of t is acceleration again, so that would just be v prime. So for this one here, so I just need to take that derivative, so I'm going to do v prime. And so this derivative, so there's like an implied one here, so negative 24 times 1 is negative 24. And then subtract 1 off the power, so that'd be 0, and the derivative constant is 0. So t to the 0, so that would be a of t, let me write it like that. A of t would be t to the 0 is 1 times negative 24, so that would be negative 24. So we would say acceleration is constant, right, because there's no variable attached with that. Okay. All right, so let's do just one more example. Okay. So this one right here, so what we're going to be taking a look at is we'll do given just a velocity graph. So given a velocity, or equation, I mean. So we'll say our velocity equation is, let's do, I don't know, t minus 6, and we'll do 3t minus 5. So we'll say that's our velocity equation. So we have some particle out there. Everything in calculus is a particle. Like your application classes are like your physics classes. But calculus, we don't get fancy at all. We just say there's a particle out there. Ooh, mysterious. And here is the velocity function for that mysterious particle. And now let's answer some questions about this particle we know nothing about. Okay, so, all right, so here would be a question. So we would want to know, when is the particle resting? So the particle is resting. And we want to know where that is happening. So I'm going to put a question mark there so it sounds like a question. Particle is resting. Okay, so here we go. So when would the particle be resting? So just a reminder, that would be when our velocity is equal to 0, right? Velocity equal to 0. So looky there, there's our equation. So I just need to set that velocity equal to 0. So I have t minus 6, 3t minus 5 equal that to 0. And then we're going to use 0 product property. So I'm going to take t minus 6 equal it to 0 and then solve. So that would be t equals 6. And then we do the same thing over here, 3t minus 5 equal to 0, and then solve that equation. So I would add 5 over and divide by 3. So when is the particle resting? So that would be at t equals 5/3. I'm going to put that one first because it's smaller, and 6. And there's no units attached to this at all, maybe seconds, maybe years, who knows. So that would be when the particle is resting. All right, and here is the very last question. When is the particle moving left? So when is the particle moving left? So it is moving left when that velocity was negative. So when is that particle moving left? When the velocity is negative. So here is the equation I have, right? Here's my velocity equation. So I know that it's going to be moving left when it is negative. So I know that it's resting at 5/3 and 6. So what I should know back in the heyday of Honors Math 3, so I'm going to mark, here's 5/3, wherever that is. Here is 6, right? And I know that I have in behavior, so this is 3t squared. So it's squared. So if I were to distribute this out, right, so that means it's equal. So I have a quadratic, right, quadratic. So that means it's equal, and it's positive, right, because there's no negatives here. So positive and equal. So that means it's got to go up on the left, up on the right, and then right there, right? So that would be the graph of my quadratic. I don't care how low it goes. I just know that would be the graph. That's a terrible parabola, by the way. I hate that this is being recorded. So anyway, that is my parabola. So pretend it's symmetrical. So it goes through the values 5/3 and 6 because that's when it's 0, right? So this is when it's equal to 0, right? So at 5/3 and 6, I have my zeros, right? And this is v of t. Let me label my axes there. So when is velocity negative? So remember, that is when it's like below, right? So that would be below the x-axis, right? So that's what we're saying when velocity is negative. So this is my v of t. It's negative when it's down here somewhere. So that would be right here. So it is moving left on the interval. So I'm going to just write left on the interval from 5/3 to 6. And then I'm going to use parentheses because at 5/3, it's not moving at all. It's resting. And then at 6, it's also resting. So I would use open intervals. And like, let's say I had to ask something like, when is it moving right? Well, that would be when it's above, right? So that would be greater than 6. So I would have said 6 to infinity, right? And then over here, if t is time, I certainly wouldn't say from negative infinity to 5/3 because that would be weird. How about from 0 to 5/3? Because I mean, in negative time, whatever that might be an Einstein question, then we would also be moving left as well. All right? I mean, right. We would be moving right as well. All right, that's it for this first lesson.